In 1997, two researchers in Munich published a paper called Long Short-Term Memory. Sepp Hochreiter and Jürgen Schmidhuber, same Hochreiter who diagnosed the vanishing gradient 6 years earlier. They proposed a redesigned RNN cell with gates, little switches that decide what to keep and what to throw away. Explicit learned. The world ignored the paper for 15 years. Then, in 2016, Google Translate switched to LSTMs overnight, and they became famous. Last video, RNNs. Right shape, wrong dynamics, memory that leaked because gradients vanished exponentially through time. This video, the fix. Not a mathematical trick. Engineering. A cell with explicit control over what it keeps and what it forgets, and a specific reason why that fixes the vanishing gradient. That's what we're here to unpack. V3 left us with a specific diagnosis. RNNs have one hidden state, updated every step by multiplying through the same weight matrix. Values under 1. Gradient dies exponentially backward. The network cannot see past about 5 words. For English, where a subject noun and its verb can sit 20 words apart, that's fatal. Today's puzzle. If the problem is that gradients get squashed by passing through many nonlinearities and matrix multiplies, can you route some information around all that? Give it a highway. Skip the crushing. Only let the network touch that information when it needs to. That's the LSTM's whole conceptual move. Today's 3 beats. First, the LSTM cell. The 3 gates. Forget, input, output, what each one does, in plain language. Second, why gates fix vanishing gradients. Not just they help, the specific mathematical reason. Third, the 15-year gap. Why nobody cared in 1997, and why Google Translate switching to LSTMs in 2016 made them briefly the most important architecture in NLP. Beat 1. The LSTM cell. There's a picture that always shows up in textbooks, and it looks terrifying. A box with a bunch of colored gates and arrows. Ignore it for a second. The idea is simpler. There's a horizontal line running through the cell, called the cell state. Think of it as a conveyor belt. It carries whatever the network wants to remember, from time step to time step, with minimal modification. Now the 3 gates that touch that belt. Gate 1, the forget gate. At every time step, the network looks at what's on the belt and decides, for each piece of information, should I keep this? A sigmoid function outputs a number between 0 and 1 for every dimension of the cell state. 0 means throw it out. 1 means keep it. In between, keep it partially. That's the forget gate. Gate 2, the input gate. Same idea, opposite direction. The network decides which parts of the current input to write onto the belt. Sigmoid outputs another set of 0 to 1 values. Multiply by a candidate update, add to the belt. Gate 3, the output gate, decides which parts of the current cell state to read out as the hidden state for the next step. 3 gates, 3 learned decisions. Forget, write, read. Beat 2. Why gates fix vanishing gradients. Here's the key insight. The cell state updates by addition, not by matrix multiplication through a nonlinearity. The forget gate multiplies the previous cell state by a value between 0 and 1. The input gate multiplies the candidate update by a value between 0 and 1. Then those two things add together. Addition, not another matrix multiply squishing everything through its hand. Why does that matter for the gradient? When you backprop through addition, the gradient just flows through, unchanged, no shrinking. When the forget gate is set close to 1, the cell state at time step 50 can carry gradient information back to time step 1 without exponential decay. The network can learn to keep the gate open when it needs long-term memory. That's the whole gradient story of the LSTM. One more subtlety. The original 1997 paper didn't actually have the forget gate. That came in 2000. Gers, Schmidhuber, and Cummins added it, and the modern LSTM you see in every textbook is really the 2000 version, which is a nice reminder. Even the paper that solved the problem needed a follow-up patch 3 years later. Engineering never happens in one paper. Beat 3. The 15-year gap. 1997. The LSTM paper comes out, barely cited for years. GPUs weren't fast enough to train them at scale. And frankly, the paper is dense, long, hard to read. Most researchers looked at it and moved on. Schmidhuber has spent his career correctly frustrated that nobody read his lab's work early enough, and he's not entirely wrong. Then, 2014, Sutskever, Vinyals, and Le at Google publish Sequence to Sequence. An LSTM reads a French sentence into a fixed vector, another LSTM decodes it into English. Machine translation using LSTMs end-to-end. Suddenly the paper is essential reading. 2016. Google Translate switches its production system to LSTMs, Wu et al. Paper. Overnight translation quality jumps for hundreds of millions of users. The LSTM is briefly the most important architecture in NLP. The catch. That was 2016. And by 2017, 1 year later, the attention paper landed and started killing LSTMs, which is why this video, and next video, and the video after all belong to Lecture 6. The LSTM peak lasted about 18 months, long enough to change Google Translate, not long enough to become the permanent answer. Video 5 is where the transformer walks in. 3 takeaways before the quiz. 1. An LSTM is an RNN cell with a cell state conveyor belt and 3 gates. Forget, input, output. Each gate outputs a sigmoid between 0 and 1, letting the network learn what to keep, what to write, what to read. 2. The cell state updates by addition, not by matrix multiply through nonlinearity. Addition passes the gradient through unchanged. That's the specific reason gates fix vanishing gradients. 3. Hochreiter Schmidhuber, 1997. Ignored for 15 years. Then Sutskever Sektua 2014, Google Translate 2016. Peak LSTM lasted 18 months before the transformer arrived. Quiz 1. What are the 3 gates in a standard modern LSTM cell? A read, write, delete. B. Forget, input, output. C. Encoder, decoder, attention. Or D. Query, key, value. B. Forget, input, output. Each gate outputs a sigmoid between 0 and 1, a learned decision per dimension about what to keep, what to write, what to read. Note the forget gate was actually added in 2000 by Gers, Schmidhuber, and Cummins. The original 1997 paper didn't have it. Quiz 2. Why do LSTM gates fix the vanishing gradient problem? A. Because sigmoid is nicer than tan. B. Because the cell state updates by addition, not by matrix multiply through a nonlinearity. So gradients flow through addition unchanged and can propagate over many time steps when the forget gate is close to 1. C. Because LSTMs use more parameters. Or D. Because LSTMs skip back propagation entirely. B. This is the whole story. Addition, not another matmul. The gradient passes through the plus sign untouched. The forget gate being learnable means the network can keep the gate open when it needs long-range memory. Quiz 3. When did LSTMs go from academic curiosity to mainstream production, and why? A. 1997, immediately after the original paper. B. 2014-2016, Sutskever Sektua Sek work in Google Translate, switching to an LSTM BASCD system. In 2016, Wu et al. C. 2020, with the release of GPT-3. Or D. They never became mainstream. B. The paper sat mostly ignored for 15 years. Sektua Siu in 2014 made LSTMs the encoder-decoder default. Google Translate switching in 2016 gave them their production moment. And the transformer arrived in 2017, so peak LSTM lasted about 18 months. Back to the puzzle. Lecture 6 is the story of how deep learning 8 NLP RNNs almost got there. LSTMs fixed the memory. Sequence models finally worked. Then, one paper in 2017, everything changed again. Next video. The paper. The 8-author bomb dropped by a Google Brain team. Attention is all you need. Next time, the 2017 paper. Attention is all you need. Vaswani and 7 co-authors at Google. A model with no recurrence, no LSTM cells, no gates, just attention, and it beat everything. That paper is where GPT starts. Hit subscribe.